Hello and welcome to this talk about the topology of the art gallery problem. I'm Simon, and the second part of this talk will be presented by Daniel. So first off, the art gallery problem is a very important problem in computational geometry, and it can be stated as follows. You are given a polygon P, and you are supposed to find a placement of a minimum number of guards, which are points inside of the polygon, which can guard the whole polygon together. So what do we mean by guarding? Well, if we have this example polygon here, and we place a guard at this black point there, it can guard the whole area that is shaded green. Because from the point, you can see to all of this area without having to look through a wall of the polygon. But the point cannot, or this guard cannot see these red tips of these corners here, because its view is obstructed by the border of the polygon. And here we can also see that for this polygon here, a single guard does not suffice. So there is no single point of this polygon from which every part of the polygon is visible. But we can also see that two guards can together guard the whole polygon. So an optimal solution for this art gallery problem here would be any assignment of two such points that together guard the whole polygon. And now if we look at the solution here, we can actually notice something, and that is that this left guard there can be moved up or down along this dashed line, and we still have a valid solution. In fact, if we move it down to this intersection of the two dashed lines, we can then also move the right point upwards, and so on and so forth until we come back to our starting solution. So somehow there is some kind of circular structure within this space of all solutions. And these structures are what we want to study in this talk. And to formalize this, we first say what we mean by the solution space. So the solution space we just define as the set of all optimal guard placements for some polygon P. And now, such that we can work with the solution space in a more formal way, we have to make this a metric space or a topological space. And to do this, we use the Hausdorff distance. And the Hausdorff distance is just a very classical way to compare two unlabeled sets of points in the plane, or in any dimension, actually. And the Hausdorff distance, intuitively, is just the maximum over all points of two point sets. And for each point, we take the minimum distance to a point in the other set. So here, from all crosses, the cross on the bottom is the furthest away from any point, and its closest point is the one on the left. And for the points vice versa, the point that is the furthest away from any cross is the one on top, and its closest cross is the one on the bottom right of it. And now the Hausdorff distance between these two sets is just the maximum of these two dash distances here. So we have this bottom distance being the Hausdorff distance here. So this is just a very natural way of comparing two sets. And with this, we can now analyze our solution space. And what we would like, or what we would find interesting, is that if our solution space was homotopy-universal. So we call a problem homotopy-universal if for any semi-algebraic set, we can find a problem instance such that the solution space of this problem is then homotopy equivalent to this semi-algebraic set. And now, for those who don't know, a semi-algebraic set is just a union of intersections of polynomial equalities and inequalities. So this is a very strong notion, and a semi-algebraic set can really take on any kind of shape that you can think of. And now, homotopy-universality would be a kind of a useless concept if there weren't any problems that were actually homotopy-universal. So there is a very famous result by Neff from 1988, and he proved that order-type realizability is actually homotopy-universal. So this is really an interesting property that we can study in the context of other problems as well. Now, homotopy-universality is closely related to another concept, which is the existential fear of the reals. Now, the existential fear of the reals, or also ETR, is both a computational problem, but also a complexity class. Now, as a problem, it is just about solving the question whether for a given set of polynomial equalities and inequalities, whether there is a real solution. Now, equivalently, we can also say that the ETR problem is to decide whether a certain semi-algebraic set is empty or non-empty. And now the complexity class based on this problem is just a set of all problems that can be reduced to this ETR problem. And now, very often, it is actually the case that if a problem is hard for this complexity class, that it is then also homotopy universal and vice versa. But we will actually see that this is indeed not always the case. Now, in the context of the art gallery problem, we have a result due to Abrahamsen, Adamaszek, and Miltzow in 2018, who proved that the art gallery problem is ETR hard. And they also proved some weaker solution space universality statement for this problem, but they did not quite reach full homotopy universality. And their proof already took over 60 pages, and it is very technical. So what we aimed to do was to actually get to a full homotopy universality with a much simpler proof. And we did this. So this is now the next part of this talk. So how do we prove homotopy universality? Well, for any semi-algebraic set, we need to find a certain art gallery polygon such that the solution space of this polygon is then homotopy equivalent to this semi-algebraic set. And to do this, we first take a few detours. So in the first step, we apply a result due to Hironaka and Hoffman, which says that any semi-algebraic set can be triangulated into a simplicial complex. Then we apply a result due to Blas and Tolzhinsky, which says that we can refine a simplicial complex into a cubical complex, and then even refine it further into a union of faces of the hypercube. And now all three of these steps are indeed not only homotopy equivalent, but even homeomorphic. But on the other hand, they can introduce quite a lot of complexity. So it is not necessarily given that this final union of faces of the hypercube is polynomially sized in terms of the semi-algebraic set that we started with. Now, a union of faces of the hypercube is much easier to work with than a semi-algebraic set, because now it is not defined anymore by polynomial equalities and inequalities, but we can actually describe it as a simple logical formula. So from each union of faces of the hypercube, we can easily write a disjunctive normal form formula. So for each maximal face in the cube, we just create one clause, and this clause describes all points in this face. So for example, for the orange face, we have this formula x2 equals 1 and x3 equals 0. And now to actually be able to translate this into an art gallery polygon, we need to take one last step, and that is to translate this into a conjunctive normal form. And to do this, we just add another variable for each clause of our DNF formula, which are these S1 up to S3 in this example. And then we end up with a conjunctive normal form formula where each clause, except this last special clause that says that one of these additional variables has to be false, each other clause has exactly the same shape. And it is always of the shape that some variable is set to either 0 or 1, or one of our additional variables is true. And this is now what we finally translate into our polygon. And to do this, we first need a way to encode variables. And for that, we have this gadget that you can see here, and this will reside at the top of our art gallery polygon. Now, this gadget is shaped in such a way that if there is a single guard within the gadget, and this guard is supposed to guard the whole gadget on its own, then this guard has to stand exactly on this dashed segment here. And now, if this guard stands on the leftmost point of the segment, we say that the variable is 0, and if it stands at the rightmost point, we say that the variable is 1. Obviously, any position in the middle is just linearly mapped onto this interval. So now for each variable of our hypercube, so for each dimension, we add one of these variable gadgets. And then we also have our m additional variables. And for these, we only add m-1 such gadgets. And we interpret these in a bit of a different way. So we say that some additional variable, for example, S2 here, we consider this variable to be true if the guard on its left stands at the rightmost endpoint, or if the guard on its right stands at its leftmost endpoint. So still, each guard can only make one variable true, but it's not quite a mapping of one guard to one variable. But because only m-1 guards are used and each guard can only make one variable true, we already naturally encode this last clause of our CNF formula, which says that at least one of these variables has to be false. So now the only thing that we need to do is encode all of these other clauses that are all of the same shape. And here, basically, these inputs, so our first input, which is here in this example, x2 equals 1, this just corresponds to a guard position, namely exactly the position where a guard has to stand to make this variable have the value 1. And similarly, the term s2 is true can now translate to an interval, and this interval as its right endpoint and its left endpoint have exactly these 2 points where guards can stand to make s2 true. And now on the bottom of the polygon, we make a small hole into our border, and this is kind of the hole of a pinhole camera. And we draw our visibility lines from our green areas through this hole. And on the bottom, we then draw this gadget. And this gadget is shaped in such a way such that, first off, we know that there needs to be an additional guard in there, because there needs to be a guard on this dashed segment. And also, this gadget has 2 corridors on the bottom. And our additional guard on the dashed segment can only watch one of these corridors at once. So if this whole gadget should be guarded with just one additional guard inside of it, then one of these corridors has to be guarded by a different guard, which is going to be a guard on either of our green areas. So we know that this gadget can be guarded with one additional guard if and only if there is at least one guard on one of our green areas, which is exactly encoding the constraint that we want to have. So now if we put all of this together, we get this following complete R-gallery polygon. And to help you understand this a bit, I have added one example solution for this. And this solution now corresponds to a certain point in our hypercube, which is in this orange phase that I showed previously, where x2 equals to 1 and x3 equals to 0. And now all of our other guards, so our guards for the additional variables and for inside of the gadgets, are placed in such a way such that for each of our clauses, there is always at least one satisfying term. And you can see that this translates to one guard on the top seeing into one of the corridors. For example, for this corridor is guarded by this guard up here. And then the guard inside of the gadget is watching the other corridor. Now, finally, let us analyze the solution space of this. So it should be clear that the positions of the variable encoding guards can now correspond one-to-one to points in the hypercube. And due to the way that we constructed the gadgets on the bottom, we know that such an assignment of our variable encoding guards can only be extended to a valid optimal solution if this point in the hypercube actually belongs to our union of hypercube faces that we wanted to encode. And all of the remaining degrees of freedom that we introduced with our additional guards can be collapsed. And to do that, we use a smallest Vietoris mapping theorem. And this then just guarantees us homotopy equivalence to our desired union of hypercube faces, and therefore also to our desired semi-algebraic set. So as a conclusion, we saw that we can prove homotopy-universality quite quickly and much easier than if we had to show full existential theory of the real's hardness. And indeed, I would like to stress again that we did not prove ETR hardness, because when we translated our semi-algebraic set into our union of hypercube faces, we introduced potentially exponential complexity, and therefore this is not a proper reduction. Interestingly enough, our proof even works for a simpler version of the art gallery problem, so the vertex art gallery problem, where guards can still stand anywhere, but they only have to guard all of the vertices of the polygon. And this version of the problem is indeed in NP, so it is at most NP complete. And this shows that homotopy universality does not necessarily imply ETR hardness, because a problem could not be NP complete and ETR hard unless these two clauses were the same, which is assumed to be false.
After we have seen how to get from any semi-algebraic set to an art gallery, we will go back to the very beginning and analyze whether this is best possible or whether we can reach even better solutions. So at the very beginning, we have seen that we can move guards, namely if we move the left guard here, up or down, then we at some point can move the right guard and so on. And at some point we reach the state where we started at. So we see that the solution space contains a circle. So if we can show that the whole solution space is this circle, then we would not only have a homotopy equivalent, but we would even have a homomorphism between the solution space and the circle as a topological space. Now, unfortunately, in this very instance of the art gallery, this is not yet the case. And in particular, the red extensions of the guard segments in the middle here, we can put guards there. So we can put a guard in the lower left corner of the triangle, and we can put a guard on the extension of the right line segment so that the whole polygon is guarded, and hence this is a solution to this polygon, to the art gallery problem in this polygon. And so we would like to avoid this to get to a homomorphism. And there is a simple way how to avoid that, and that is by reconsidering how we did this, how we built these guard segments, namely by reconsidering the pockets we used so far. And so far we used pockets on the left and on the right, namely one pocket on the left open to the above and one pocket on the right open to the below, so that the middle, the guard segment, is where a guard needs to stand if he wants to see both pockets. However, as we have seen, he does not need to stand on the very middle, but he can also stand on the extension of the guard segment. And to avoid that, we can update our idea. Namely, we can add 2 additional pockets so that whenever a guard stands on the guard segment, on the black dashed guard segment, then he sees all 4 pockets. However, when he stands on the red extensions, then he does not see these additional pockets. And with this, we know that whenever we have this blue area and there is a single guard in this blue area, then he needs to stand on this dashed guard segment as planned. And hence, if we update our polygon, then we indeed know that all solutions to this art gallery instance have all their guards on the triangle in the middle. And so we have a guard, a polygon with guards, so that the solution space to this polygon is homomorphic to the circle. Now, not only can we get solution spaces homomorphic to the circle, but we can reach different topological spaces, for example, clovers, chains, necklaces, but also spheres in any dimension now, and also the torus and the double torus. And in the remainder of this presentation, we will go into detail about how we reach spheres and how we reach a torus. Now for the sphere, or the one sphere to begin with, or namely the circle, we have already seen how to construct it, but we use a slightly different construction now. Namely, we study the grid. So we have guard segments, namely 3 horizontal guard segments, where on each of these horizontal guard segments, one guard needs to stand. And we have 2 vertical ones on the left and on the right, where again, on each of those guard segments, there needs to be a guard. Now, so far we forget about the polygon as is and only consider these guard segments. And we see that with these guard segments, we also get a circle. And one way to see this is we can name the guards, namely, for example, the topmost guard as guard A, the second one as guard B, and the third one as guard C. And we can embed all solutions in this 3-dimensional hypercube. And we see that indeed all solutions form this circle. Now to get to higher dimensional spheres, we do a slight detour, namely we first study the disk or the 2-ball. Namely, what happens if we forget about one of the vertical guard segments? So instead of considering a 3x2 grid, we consider a 3x1 grid. And one very obvious thing comes to mind directly, namely there is a solution that was not there before. And of course, all solutions that we had before, they still are valid in this setting, as we have strictly fewer conditions on where to place guards. Now we again can embed this thing into the hypercube. And now where does this middle solution lie, the one where all guards stand on the right-hand side? Well, this lies in the top far right corner. And we also notice that all the solutions corresponding to the top face and all solutions corresponding to the behind face and the right face of this cube are indeed valid solutions to this grid. And we indeed get a 2-ball or a disk, respectively. Now to go on, we just add guard segments to our grid. So instead of having a 3x2 grid, we now consider a 4x2 grid. And this will indeed show that we get the sphere. So we have 4 guards, they stand somewhere on our grid. And to see that we not only can work with these grids, but we can indeed have a polygon. I have drawn a polygon here. And to see that this is indeed a 2-sphere, we will watch a short video. So on the left-hand side, you again see the polygon we had before. And now think of the first guard, namely guard A, as fixed, somewhere in the middle. And now the other 3 guards, we know what happens here. They form a 3x2 grid. So this is homomorphic to a circle. Now, once we are in a configuration where both vertical guard segments are guarded, we can move guard A to one of the sides. And once it's there, we can completely forget about the vertical guard segment it guards, and guards B, C, and D, well, they form a 3x1 grid now, which we already know as a disk. So this indeed forms a solution space that is homeomorphic to the cylinder here, which of course is now a 2-sphere. So going back to different ideas. So instead of using grids, let's try to get the torus. And for the torus, we notice one important ingredient, namely a torus is the Cartesian product of 2 circles. And if we have the triangles completely independent of one another, as for example here, then of course our solution space is the Cartesian product of the 2 different solution spaces, meaning this already gives us a torus. The double torus, however, is harder to explain. And for the double torus, we again watch a video. So again, on the left-hand side, you can see the polygon as we had it before. Some regions are colored, some regions are not. And if we move the guards on the left-hand side, then this forms a torus. Now we can move the lower guards or the upper guards somewhat independently. The only restriction is that in the gray area, the one coming from the above pocket, there we always need 1 guard, and so it's a bit restricted. Namely, there is a region on our torus where we are somewhat on the boundary. And if we are there, then we can move also the guards on the right-hand side to switch the torus. And once we switched, we are again in the same situation as before, just symmetrically. And we can indeed see that this is the double torus. And with this, let me conclude what we have seen. So we have seen a simple proof of homotopy-universality of the art gallery problem. And for some topological spaces, we have even seen homomorphisms between the art gallery instance and the solution space. And with this, let me conclude with 2 open questions, namely, what about homomorphism universality? So for any semi-algebraic set, is there an art gallery where we can not only show homotopy equivalence, but also homomorphisms? And maybe what you can think about in the next coffee break or when you eat dinner or lunch, like what happens if I want to reach an unorientable surface? is there a simple polygon that I can draw such that my solution space is unorientable in the end? So thank you for listening and see you soon.